हेलो उषा मैम।
ना ना ऐसा मत।
अरे
उषा मैम गुड आफ्टरनून, मेरी आवाज आप तक पहुंच रही है?
हाँ जी पहुंच रही है।
हाँ जी मैम, गुड आफ्टरनून।
गुड आफ्टरनून
मैम सर किस समय ज्वाइन करेंगे?
प्रिंसिपल सर।
हाँ
पता नहीं, आपने नहीं पूछा।
चलिए मैं एक बार रिमाइंड कराता हूँ
बात
सर।
कर।
हाँ हाँ
हाँ हेलो, शुरू कर दिया है ना? चलो आप, हाँ 29 पार्टिसिपेंट्स आ भी गए हैं।
हरेंद्र मैम नमस्कार।
हाँ हाँ, वो मैंने किया हुआ है ना। हम्म।
नाउ सर हैज कम। मैम सर आ चुके हैं।
बट अभी वो आई नहीं ना हमारे प्रोफेसर के श्रीनिवास।
हरिंद्र मैम, हरिंद्र मैम।
हाँ जी, बोलो बोलो।
एक बार सर को रिमाइंड कर दीजिए, ज्वाइन कर ले।
एक्चुअली सर ना अभी कॉन्फ्रेंस से बिजी हैं।
ओके
तो वो जब टाइम मिलेगा वो ज्वाइन कर लेंगे।
तो फिर
हम
उनको,
इसको
आपने कहा
हम
था कि
इसको
उनको
हाँ
बुलाना है।
हाँ, नहीं आप देख लो, जैसे ही वो ज्वाइन करेंगे तो उनको बुला लेना, नहीं तो जो अभय सर है उनको बुला लेना आप।
तो अबे सर भी तो अभी ज्वाइन नहीं किया ना।
हाँ हाँ, कर लेंगे ज्वाइन अभी।
हाँ चलो 2 मिनट वेट
अभी
करते
4:25 है ना।
हाँ 5 मिनट
हाँ
वेट।
हाँ
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 हाँ।
हाँ ओके।
diagram E बता दी
हेलो उषा मैम, अभय सर ने ज्वाइन कर लिया है मैम।
I know, but should we start, Harindri? We can start now. Harindri, can we start now?
Yes, ma'am. Yes, ma'am.
Yes, ma'am. Start कर सकते हैं. Yes, ma'am. Please start.
Am I audible to everyone?
Yes. Yes, ma'am.
Okay. चारों तरफ हो खुशियों की लहर, हर तरफ चलता गुणगान रहे, बरसे असीम अनुकंपा ईश्वर की, आपके होठों पे सदा मुस्कान रहे. Good evening, namaste, abhinandan, and thank you all for joining us in this inaugural session of online teachers enrichment workshop on differential equation and its application, a joint program of Indian National Science Academy and National Center for Mathematics, being organized here by Department of Mathematics, and IQAC Deshbandhu College. World is full of diamonds and gems. We are having today some of them to build this event. On behalf of the Department of Mathematics and IQAC, who has clubbed all of us here, I extend a very warm welcome to one and all present here and all the participants. I have special welcome to you that you have joined here timely, and they are all from University of Delhi, and not from University of Delhi, but other colleges of different universities across India. We are grateful to Professor K. Srinivas and Professor Abhay Bhatt for guiding us every time to organize this workshop. Professor Abhay Bhatt is here. I feel my deep sense of gratitude to him for taking time off from his schedule to join us and grace the occasion. We welcome you, sir. Now, we express our sincere gratitude to you for your constant support and organized workshop. Yes. Friends, such events or such workshops do not happen overnight. It takes months of planning to organize such events. I am pleased to thank the hard work, patience, and perseverance of our principal, Professor Rajiv Agarwal, for his day-to-day guidance in the execution of this event so well. Without his guidance, we would not have been here today. Appreciating the untiring efforts, I congratulate our convener, Dr. Harindri Chaudhary, our teacher in charge, Dr. Chandrasekhar, and all the members of organizing team for the successful launch of this program today. I also give my sincere gratitude to Dr. Aditya Saxena, IQAC coordinator, and Dr. Monica Bajaj for their support at all the fronts. Now, coming back to our tradition, we take the blessing of Ma Saraswati, who is the goddess of learning, intellect, and wisdom. And for this, we take the blessing and pray for the success of this event so well. Now, please join us for the virtual lamp lightning and Saraswati Vandana.
बाबू आधार मंगल लिखा हुआ है। ठंडी हवा खा रहे हो? फुल ठंडी हवा खा रहे हो?
ये भगवान मच्छर आते हैं तो ये करते शू शू ऐसे
May Goddess bless us all and make this event successful. It's of course 14 days program, so we have to be there every day from 5 to 7 for 2 lectures. Now, a revered mathematician, distinguished young educator, a great researcher, an excellent administrator, who is none other than our principal, Professor Rajiv Agarwal. I know he needs no introduction, but I take this privilege. He joined this college in 2018, and in a short span of 3 years, he has taken the college to new heights. And of course, he has given a very good facelift to our college. Today, I'm proud to announce that Deshbandhu is among one of the very few colleges of Delhi University who has finished all the screening committees for the long pending promotions of its teaching staff. It's all because of your dedication and passion and, of course, upliftment of the college. We salute you, sir. And of course, besides this interest of academic interest, his excellent administration is there. Now I will invite him for a formal welcome address. Dr. Rajiv Agarwal, over to you, sir.
Thank you, Dr. Usha Arora. So this introduction was not related to our workshop. So very good afternoon and namaskar. On behalf of Deshbandhu College, University of Delhi, I welcome our esteemed guest today, Professor K. Srinivas, IMSC Chennai, presently convener Tew program. Professor Abhay Bhatt, ISI Delhi, workshop convener. Ms. Harindri Chaudhary, convener of the workshop. All dear friends from Deshbandhu College, the esteemed faculty members, and all the participants from different prestigious institutes from Delhi and across India. In this Teachers Enrichment Program Tew on differential equations and its application, which is jointly organized by Department of Mathematics, Deshbandhu College, and National Center for Mathematics, which is a joint venture of TIFR and IIT Bombay. I especially welcome our esteemed resource persons, Professor V.D. Sharma from IIT Gandhinagar, Professor Rashmi Bharadwaj from Guru Gobind Singh Indraprasth University, New Delhi, Professor Malay Banerjee, IIT Kanpur, Professor Navneet Jha, South Asian University, New Delhi, Professor Kapil Sharma from South Asian University, New Delhi. You can see from their names how influential, how they are expert in their fields. Friends, this Teachers Enrichment Program or workshop is a program funded by National Center for Mathematics. This Tew is basically meant for college teachers to revisit and update their content knowledge. The lectures in this workshop covers specific topics which are relevant for teachers' classroom instructions. An important component of this program is the discussion hour, during which teachers will have opportunities to get their doubts cleared and work out routine to advanced exercises. The topic of the workshop, this particular workshop, is differential equations and its applications, which is very interesting and rather worthy. The study of differential equations has numerous applications in pure as well as applied mathematics, physics, engineering, and even in social sciences, medical sciences, biomedical sciences, and in various other fields. All these disciplines are concerned with the properties of differential equations of various types. Differential equations play an important role in modeling virtually every physical, technical, or biological process, from celestial motion to bridge design to interaction between neurons. Differential equations such as those used to solve real life problems may not necessarily be directly solvable. That is, do not have closed form solutions. Instead, solutions can be approximated using numerical methods. A brief idea of the topics which are likely to be covered by our esteemed resource persons and under this workshop are first order differential equations, growth and decay model, Euler's equation, power series solutions of a differential equation about an ordinary point, nonlinear autonomous system, equilibrium point and their stabilities, bifurcation, cycles, Lyapunov function, chaos, Lyapunov exponents, general solution of system of nonlinear equations, stable manifold theorem, Hartman-Dobeman theorem, introduction to radial basis functions, thin plate spline, piecewise smooth, and various other topics. This workshop is not only limited to these topics, there are many applications of differential equations in various scientific areas. I hope our esteemed experts, resource persons will enlighten us on these applications. In the end, before I conclude, I would like to congratulate the whole team of this workshop and give my best wishes to the Department of Mathematics of our college, conveners of this webinar, Professor Abhay Bhatt, Mrs. Harindri Chaudhary, Associate Professor, Deshbandhu College, teacher in charge, Mr. Chandrasekhar, our dynamic IQAC coordinator, Dr. Aditya Saxena, and all the faculty members of Mathematics Department for organizing such a wonderful event. My best wishes for this event. Thank you very much. Dr. Usha, over to you.
Thank you, sir, for explaining the importance of this teaching and teachers enrichment workshop. And of course, explaining the topics because they are close to your heart. You are also the specialist in this. So I just came to know that Professor K. Srinivas has just joined us. So what makes a good teacher great? I think teacher is a lifelong learner. And we are honored to have among us Professor K. Srinivas, the convener of National Center of Mathematics NCM Program Committee for Teachers Enrichment Workshop. So he can tell us about the importance and why we are doing this all about this. And we are also grateful to him for his constant support in the organization of this event so well. Having his research interest and several publications in the field of analytic number theory, algebraic number theory, and mathematical aspect of cryptography, he is Professor of Mathematics in Institute of Mathematical Sciences, Chennai. I request him to say a few words to our participants. Over to you, sir, Professor K. Srinivas. Sir, your mic is mute. I think, sir, your mic is mute.
Hello. Can you hear me now?
Yes, sir. Yes, sir.
Oh, good. Great. Yeah. So thank you very much for inviting me to be in this program to address you all. Actually, Professor Abhay Bhatt is also a part of this NCM thing, so it was not very difficult when Harindri ji approached us with her proposal, and we saw that it is very good. And we have already had some programs in Deshbandhu College before also, so it was a smooth run. All right, and the speakers are pretty good. We are really thankful for them, who have agreed. So I would not like to take much time, but this NCM, this TEW programs, they will not be like, your usual classroom kind of talks, something different, something other than what you learn in the classrooms. Some historical things also, I mean, who are the people who have invented all these things? जैसे कहा जाता है ना कि जी रहे हो जिस कला का नाम लेकर, जानते भी हो कि वो कैसी बची है, सभ्यता के जिस अटारी पर खड़े हो, ये वही गुमनाम लोगों ने रची है। तो इस तरह के वाकयात, इस तरह के वारदात, इस तरह के जो है जुमले, किस्से सुनने मिलेंगे शायद। तो उम्मीद है कि प्रोग्राम जो है पार्टिसिपेंट्स को के लिए कुछ मतलब नए किस्म के माने टीचिंग मेथड्स, हाउ टू टीच इन ए बेटर वे, हाउ टू अंडरस्टैंड, हाउ टू डेवलप the skills of problem solving. The emphasis will be more on problem solving, and also how subjects are interrelated. Okay, so these kind of things are the main emphasis of this program, and I'm very happy to see that Harindra ji has done a wonderful job. So I request all the participants that, since it's an online program, it will not be clear for teachers who are present and who are not present, but there is a belief. We believe that, all of you are present, you are sitting with a pen and paper and you are working out the things that are being given. This is a serious program and we encourage only those who are interested genuinely to be part of this program. And we hope all of you are interested in this. So I wish you all the best. I wish the organizers a success, and I wish the participants, to have a very good and meaningful time in this, 2 weeks time, whatever you have. So since I'm already attending another conference, I won't be able to talk more, and I will leave it to you organizers and speakers to kind of proceed with the program. Thank you very much for inviting me. Thank you very much.
Thank you, sir.
Thank you, sir. Thank you, sir, for finding time out of your busy schedule to join us and grace the occasion. And as you said, that I hope that our participant will get crystal clear knowledge of all the concepts of the topics being covered in this workshop.
Sure. And it should be interactive. You see,
thank you, sir. Thank you once again for your inspiring.
Thank you very much. Bye. Bye.
As Professor K. Srinivas told us that we already have one workshop, TEW, in the year 2018. And I'm proud to say that Professor Abhay Bhatt was even then the convener for this workshop. Today he is with us, and Professor Abhay Bhatt, he is also always very supportive in the organization of any event of this kind. Like even 2018, he was there with us for all the constant support and guidance. He's convener of Tew-21 also. He is a member of Instructional School for Teachers. Is one of the NCM program committee, and Professor Abhay Bhatt is presently working in the department of ISI Delhi, and his area of his academic interest include Markov processes and martingale problems, stochastic filtering theory, and stochastic control. Now I request Professor Abhay Bhatt to address the participants. Over to you, sir.
Thank you, Dr. Arora. I first of all welcome all the participants. I also thank Professor Rajiv Agarwal, Professor Srinivas, Harindri, who is the, I would say, from my point of view, who is the driver of this particular workshop. But I'm sure, as Professor Agarwal mentioned, there is a whole team behind her, which is looking into all aspects of organizing this. Yes, I was part of the organizing committee of 2018 TU held in Deshbandhu, and the one thing which I miss is being in Deshbandhu College today. Last time I could visit. This time, for reasons all of us are very well aware of, we can't do that. So it's online. So the online mode brings forth a lot of advantages, but quite a few disadvantages. And I again would like to congratulate the Deshbandhu team to arrange this online thing. This is perhaps the way forward. In any case, Professor Agarwal and Professor Srinivas already mentioned a lot of things about NCM and Tew. So NCM actually has been running several programs aimed at researchers in mathematics, PhD students, teachers, and in general, young researchers. And TEW is one such program. So there are several programs targeted towards different audiences. Some programs for first year research scholars in mathematics, a few programs for senior research scholars, and so on. So TEW is aimed at college teachers. And the idea, as Professor Srinivas mentioned, is to look at the subjects that you are already teaching in a different, possibly a different vein, some more interesting ways of teaching, of connecting it to different areas of mathematics and so on. So I invite all of you to take this opportunity, and the final aim for this program is actually that it will percolate down to the students that you teach in your colleges. So that is the whole idea. And I hence once again invite all of you to take this opportunity to do that. I think I will, as I said, I miss, but I do thank, I miss being in Deshbandhu College. And since 2018, just one side remark I will make that Professor Agarwal and Dr. Chaudhary have, I mean, I've been contacting them in other respects also, as far as mathematics, well, NBHM and everything is concerned, and they have very readily and happily agreed to all my requests. So I thank them on that count as well. So this is also a networking that is being developed, and it's good. So I think I will stop here. I welcome all of you once again to this 2 weeks of Tew, and go ahead. Thank you.
Thank you very much for your inspiring words, sir. Of course, our principal and Dr. Harindri Chaudhary, they are a team now. Of course, you said that they are doing so well in your other associations also. Sir, keep it up. Harindri, always she's there for helping anyone. But sir, she's even so busy, even then he always finds times for doing one thing or the other for the benefit of our teachers or the college, whatever I say. Actually, I have no words to say how he works, his working style. Everything is so perfect that his work speaks volumes about his upliftment of the college, what he has done for the college. It's really remarkable. Now, I think our Professor V.D. Sharma is around, Harindri. So it's the time
Actually,
for the
actually, he's having a lecture. He'll be joining in a couple of minutes.
So in the meantime, what should you can?
So what you do, you can read out the instructions given to the participants for the Tew workshop.
So you can read out if you have write it now. You can read out.
Just a moment, I'll just check it.
I request Harindri Chaudhary to please read out the instructions for the participants during the whole workshop for all these 15 days.
If I have, I'll just check it out. Just a moment. And Rohit can take the screenshot of the participants present over here. Rohit, are you here?
Ask them. I can.
Madam, I think Rohit is not there because he is busy in examination. So Dinesh can take the screenshot of participants.
Is Shipra here?
Yes, ma'am, I'm taking the screenshot.
You can take the screenshot.
Okay,
And check who are present in this ceremony, because at 5 o'clock we will start the lecture.
Okay.
And if we will give the e-certificate only if there are more than there is more than 90% attendance of the participants. To the participants. So I read them out. So all of you are requested to kindly join every moment technical issues. Please mute yourself throughout the sessions. To ensure your vigilance, the administrator can ask you to switch on. As per the guidelines of NCM, it is mandatory to have at least 90% attendance throughout the workshop. It is mandatory to fill and submit all the feedback forms that will be shared with you during the workshop. So we'll be taking your attendance in each session. This is the first point. Second, after each speaker will be sending you a feedback form and a multiple choice question containing 10 questions. So you have to submit these two things after each speaker. Okay. So these are the few instructions. And Professor V.D. Sharma is having a lecture. He'll be joining in minutes. I just confirmed from him. So Sir is joining. He has just finished the class. So he is joining the session. Am I audible? Am I audible?
Yes.
Ma'am, yes,
हाँ
ma'am,
रोहित, तो
आपकी
सर
आवाज
ने
आ रही है।
सर को को होस्ट बनाइए वीडी शर्मा जी को.
Dinesh, Sepra ma'am.
Yes.
Yes.
Are you able?
Yes, sir, you are audible.
Oh, very nice, very nice. So let me.
Sir,
Usha ji?
hi. Sir, before you start, I want to give a brief introduction of you to the audience. An eminent mathematician, Professor V.T. Sharma, is presently a visiting professor at IIT Gandhinagar, emeritus fellow at IIT Mumbai. His legendary work experience includes former head Department of Mathematics, IIT Bombay, visiting professor at IIT Goa, institute chair professor at IIT Bombay, with nearly 100 research publications. His research interest in the field of quasi-linear system of partial differential equations, non-linear gas dynamic and shallow water waves, Lie groups invariance for solutions of partial differential equations, etc. Besides his association with many prestigious academic committees, he is a member of NCM committee for Tew, for which one workshop is being conducted here. Long list of his awards. I will just mention a few. He is recipient of President of India Award for Best Research Paper Presentation, Excellence in Teaching Award, IIT Bombay, M.N. Saha Award for Research Work in Theoretical Sciences from UGC Government of India, Professor S.T. Bhattacharya Research Excellence Award in Pure Sciences, Distinguished Services Award for his outstanding contribution to promote applications of mathematics in India, Research Dissemination Award. There are many more, but time constraint is there, so I will just put a stop over here for his achievements. And but one thing I would like to mention, that during his IT, one of his student has written in his blog, and he has given a credit to him as another god at IIT, which is always close to my heart, that he is so worshipped among his students. So now over to you, sir. Hope you will have a very enriching time with Professor V.D. Sharma. Over to you, sir.
Thanks a lot for this kind introduction. So, all right. So in this talk, I will start with first order partial differential equations. First order PDEs.
Sir, click on this full screen mode.
Yes, I will do that. I will do that.
Yes, sir.
That's okay.
So I'm sure that by the way, how many participants are there? And can you just tell me the number?
75.
Okay, all right. So you see, the first order partial differential equations, in fact, they appear in a large number of physical processes. It is well known that most of the physical phenomena, in fact, are modeled by partial differential equations. If it is higher order, it can be expressed as a system of first order partial differential equations. So in fact, a large number of physical phenomena are modeled by partial differential equations under the assumption that the variables which describe the state of a physical system are sufficiently smooth. Right? This is the assumption. For example, if suppose use the unknown function and it depends on the variables, say x and y, then it is assumed that deva u, deva x, deva u, deva y, etc. I mean, these derivatives exist, not only they exist, but they are continuous as well. So I again repeat, these first order partial differential equations appear in a large number of physical processes, right, under this assumption. But there are physical processes where this is not true. I mean, the system, in fact, breaks down after a finite time or a finite running length. No matter how smooth is the initial profile, right, your solution breaks down after a finite time or a finite, that we will talk about it, you see, a little later. But this is fact of the matter that this breakdown takes place. So anyway,
here we shall be dealing with a differential equation of this kind: f of x, y, u, ux, uy equal to 0. Here, u is the unknown function, x and y are the independent variables, ux and uy, right? These are the first partial derivatives with respect to x and y respectively. Okay, so perhaps you may recall that in an ordinary differential equation, if you are required to find the integrating factor, what do? If the differential equation is of the form, say, mxy plus nxy y dash equal to 0, and if you are, required to find the integrating factor, what we do? We multiply it by mu, and then, it reduces it to a partial differential equation. So in fact, this ordinary differential equation reduces to a partial differential equation. Here mu is the integrating factor. I multiply this differential equation by mu, right? Mu, which is a function of x and y, then it takes the form n mu x minus n mu y. This is equal to mu times my minus nx. Perhaps you may recall that now from here we get this result that under what condition, if 1 upon m minus n mu is a function of x alone or mu is a function of y alone, then we get some, right? Easily some integrating factors of a given differential equation. But you see, if you look at it, this is a first order partial differential equation. Similarly, if the function f is an analytic function, right? F is an analytic function of z, having this real and imaginary parts, we know that real and imaginary parts, they are the solutions of the Laplace equation, right? So these, we know that I just mentioned that higher order partial differential equations can be expressed as a system of first order. This we will discuss it a little later. So next we come to classification. This is important. So you see, a differential equation which is of the form a, x, y, u, a depends, this coefficient depends on x, y, and u. X and y are the independent variables, and u is the unknown function. This ux plus b, which is a function of x, y, u, uy, this is equal to c, which is a function of x, y, and u. Right? This is called quasi-linear. This is called quasi-linear, right? If the partial differential equation can be written in this form, we call it quasi-linear. We call it quasi-linear. Why it is called quasi-linear? Because it is linear in the highest order derivatives, right? It is linear in the highest order derivatives, but it is non-linear in u. U appears in this coefficient as well as it is ux. So it is non-linear in u, but linear in the highest order derivative. Such a differential equation is referred to as quasi-linear, right? If these coefficients, if the equation is of this form, a which depends only on x and y, b depends on x and y only, and c is a function of x, y, and u. This differential equation is referred to as semi-linear. So what is the definition? In a quasi-linear partial differential equation, highest order derivatives, they appear linearly. Similarly, in a quasi-linear partial differential equation, right? In a quasi-linear partial differential equation, the coefficients, they appear, they are the functions of u. They may be functions of u, and say, so had it been uxx, then yes, possibly it could have been a function of ux also. Means the coefficient functions cannot be, these coefficients a, b, etc., they cannot be functions of ux and uy, right? That is, the coefficients, they depend on u if the highest order derivative is 1. Right? If the highest order derivative is 2, then they may depend on u and ux both. So the classification says a partial differential equation is said to be quasi-linear if the coefficients of the highest order derivative terms right? Here it is ux, uy, so it depends only on u, right? X, y, and u. Semilinear. A differential equation is said to be semilinear if the coefficients of the highest order derivative terms, they neither involve u nor its derivatives. They are functions of x and y only. The right-hand side is a function. So you see, this is nonlinear, but a very special class of nonlinear. But of course, this semilinear is embedded in the class of quasi-linear partial differential equations. Now, similarly, what we say that is linear, if it is this, if it is of the form xy, uy, and it is of the form, say, c1, which is a function of xy u, plus C2, which is a function of x and y. If the different, again, it's a very special case of this, when the function C is linear. C is linear in U. So the classification is like this: quasi-linear, semi-linear, and linear. So we will talk about the nature of the solutions when it is linear, right? What is the difference when it becomes semi-linear, and what happens when it is quasi-linear? So this is we are going to discuss in this lecture. All right. So I think this classification is clear to you people, but maybe that perhaps some further examples would be necessary. For example, if I write this differential equation, uxx plus ux whole square, this is equal to 0. What is the nature? Can you tell me what is this? Is it quasi-linear, linear, semi-linear, or non-linear? What is the nature of this? Hello? Hello? U multiplied by the second derivative of u with respect to x plus ux square equal to 0. The question is this: what kind of partial differential equation is this? Of course, the order is 2, so it's a second order. But is it linear? Hello? Hello? No response from the participants?
Sir, many of the participants are saying non-linear.
No, you see, I have talked about semi-linear, quasi-linear. They are definitely non-linear, but they are not fully non-linear. They are not fully non-linear, right? That's why it is called semi-linear, it is called quasi-linear, and I have stated the definition. Semi-linear means the coefficient of the highest order derivatives, they depend only on x and y, not on u and its derivatives. Quasi-linear, what is the definition? The coefficients of the highest order derivatives, they depend on u. So definitely, if it is second order, so now based on this, what can you say about this? Is it semi-linear? Definitely it is not. What is fully non-linear? You see, the fully non-linear would be this: ux square plus uy square, this is equal to 1. For example, equation like this. This is fully non-linear. First order, this is fully non-linear, right? But of course, these equations, I mean, they are all very special cases of a fully non-linear, right? This is here, the coefficients, they depend only on the unknown functions. Here, the coefficients, they depend only on the unknown functions, but the right-hand side, it depends on u. But here, had it been second order, then we could have allowed this a and b to depend on ux as well, right? Similarly here, so based on this, their answer is what it is it fully non-linear or quasi-linear or semi-linear? What is this? My question is this: what they are saying? Hello?
Sir? Yes, sir.
What is the answer from the participants? I just wanted to know whether they have understood the definition itself or not.
Okay.
All right, if there is...
the majority of the participants have said quasi-linear.
It is quasi-linear, very right. It is quasi-linear. Yes, because the highest order derivative appears linearly, very correct, you see. The highest order derivative appears linearly, and therefore, according to this definition, it is quasi-linear. Now, if I write like this, ux plus uy, and it is multiplied by e to the power u plus sine of u. This is your uq plus x square u plus y. What is the, yes, classification? Yes, somebody tell me what is the nature of this? Hello? Hello? Again it is quasi-linear. Why? Because the highest order derivatives appear linearly. Highest order derivatives, right? You look at the functions. They depend on x, y, and u. X and y are not there, but they are the functions of u. So definitely it is an example of a quasi-linear partial differential equation. What about this if I write 2x ux minus 2y uy is equal to u plus sine y? Can you, yes, somebody should be able to tell me what is the nature of this?
It is still quasi-linear.
This is linear because you see this coefficient, look at the coefficient. They are functions of x and y. Look at the right hand side, it depends linearly on u. So it is a linear one. It's a linear equation. Am I right? But of course, non-homogeneous. Linear, non-homogeneous, right? Non-homogeneous means there is some term which neither depends on u nor its derivatives. So for example, this sine y, because of this it is non-homogeneous. All right, let us look at it. X ux plus x plus y into uy, this is equal to u square. What is the nature? As per classification, we will call it quasi-linear, non-linear, or semi-linear. Hello?
The semi-linear.
Why it is semi-linear? Very correct. It is semi-linear. The answer is correct. It is of this form. Yes, but semi is all right. If I write uy plus ux plus u triple x, third derivative. What is the nature of this? What you will call it? Hello?
Sir, it's quasi-linear.
You see, the highest order derivative appears linearly, that is true, but something more. What is that? What is the coefficient of the highest order derivative? Here the highest order derivative quasi-linear, they are the functions of x, y, and u. But if you look at the highest order derivative here, the coefficient is 1.
Yes.
Right? If the highest order derivative appears linearly, what did I say here? So definitely it is an example of a, yes, can you modify your answer?
It's linear.
Semi-linear, very right. Semi-linear. All right, so this goes, the classification is like this. Now, all right, solution, so it's very clear. So by a solution means, if I'm looking for a function which satisfies the differential equation identically, right? A function which satisfies it identically, I will call it the solution, right? I will call it the solution. But it's very clear that if it is all right, let's consider only equation, simplest equation one can think of, dy u dy x plus c naught, or let me say that, all right, I think time, I'm going to replace y coordinate by time, dy u dy t plus c naught dy u dy x. This is equal to 0, right? And there is an initial condition that at t equal to 0, u is equal to u naught of x. This is a given function, a given smooth function, given smooth function. And here x is in R and t, in fact, it is greater than 0. Right? U evolves according to this law, dy u dy t plus c naught dy u dy x. This is equal to 0. U is the unknown function. C naught is a constant which I can take to be positive without any loss of generality, C naught to be positive, and U naught is a given smooth function. You know that this is the simplest partial differential equation one can think of. Simplest. Nothing can be simple than this, right? The unknown function depends only on two independent variables, x and t, and such a differential equation is taught at the undergraduate level, right? Most of you may be knowing that what is the solution of it. Anybody can tell me what is the solution of this differential equation? Hello? Hello?
Yes, sir. Yes.
What is the solution? Can you tell me? It's a very well-known differential equation taught at the undergraduate level. In fact, this is one of the factors which appears if you think of a wave equation, you see, if you hold a string and which is fixed, okay, at the two ends, and if it is made to vibrate by pulling it into a certain shape, and if it is released from rest, it will vibrate from its main position of equilibrium, right? And the displacement at any x and t is governed by that equation. This is one of the factors, right? That is c square, this is utt, am I right? Transposing this to the left, what do you get? That is deva t minus deva x, or c times, or let's c naught, this operating on deva u deva x plus c naught deva u deva x. This is equal to 0. Is that right? I can factorize this operator. Second partial derivative with respect to t. This is second partial derivative with respect to x multiplied by c square. Transposing this to the left, I can write this differential equation in this form. So you can see here a solution of this is going to be a solution of this, right? So now can you tell me that what is the general form of the solution? Because it is taught at the undergraduate level. Anyway, we will derive it now. What is the methodology? The methodology is, it is called the method of characteristics. The method of characteristics. So what we do, we notice that there are certain curves in the xt plane. This is your xt plane, right? In the xt plane, there are certain curves, dx defined by this differential equation. Because you see, just by inspection, I can say that dx dt, if c naught is replaced by dx dt, then what is the operator? Deva t plus dx dt deva x. And what is this? It is nothing but the total derivative. So along these curves, the differential equation along dx dt is equal to c naught. The differential equation 1 becomes an ordinary differential equation. The partial differential equation 1 becomes an ordinary differential equation. What is that? du dt, this is equal to 0. Is that right? Because c naught is dx dt. So this is, since u is a function of x and t, right? Its partial derivative with respect to t plus partial derivative with respect to x into dx dt is nothing but total derivative of u. So along these curves, the partial differential equation reduces to an ordinary differential equation, and it takes the form du dt equal to 0. What does it mean? This means that along these curves, these are the curves. C naught is a constant, so quickly I can write C naught t plus xi. Xi is an arbitrary constant. That is, if xt is any point through which it is a straight line, right? C naught is constant. If this line intersects the line t equal to 0, say at x is equal to xi, this point is x is equal to xi, right? At x is equal to xi, what is the information available here? From here it is clear that at x is equal to xi, in fact it is u is your u naught xi. Is that right? The value of u at t equal to 0. At t equal to 0 means on this line, it is u naught xi. What happens along this line? So this is called the characteristic, you see. This is called the characteristic of this differential equation. That is, it's a straight line in this case. Along this line, what happens? Along this line, u remains constant. Along this curve, which is a straight line, u is equal to constant. So what is u is equal? What is that constant? Whatever is the value available here. This information is transmitted into the region along the characteristic curves. Is that right? This is your U0 of xi. This is U0 xi. Is that okay? This is a partial differential equation of first order. I find that if there are certain curves in the xt plane given by this differential equation such that along these curves which are described by this differential equation, the partial differential equation becomes an ordinary differential equation and it gives me u is equal to constant. If u is equal, so along these curves, u is equal to constant means what? Xi. Now, if I eliminate xi from these two equations, what do we get? U is equal to u0 of x minus c0 t. Because xi, transposing the c0 t to the left, xi is your x minus c0 t. Substitute it here. And this is the solution of the partial differential equation, right? Number 1. Is it all right? This is called the method of characteristics, right? That is, whatever the information is available here, this information is transmitted into the region in which we are interested in finding out the solution, right? That is, u0 xi, u is equal to u0 xi, and xi is given by this. Xi element of these two will give us the required solution. So if u0 is a given smooth function, one can quickly see that it satisfies the differential equation. That is, what is your ux? Ux will be your u0 prime. Prime means derivative with respect to this argument function. Argument function is x minus c0 t, right? This is the argument function. Multiplied by what? Derivative with respect to, so it is only 1 because this is t, right? Derivative with respect to x, taking t as fixed. So ux is this expression. What is ut? Ut will be your u0 prime. What is prime? Prime means derivative with respect to the argument function. Chain rule, we are using chain, right? Ut will be your minus c0. And from these two, yes, what do we get? If I multiply this equation by c0 and add, we get these two equations imply that ut plus c0 ux equal to 0. So you can see here that the equation is identically satisfied. Partial differential equation is identically satisfied, number 1. And number 2, at t equal to 0, now you can see here, at t equal to 0, u is equal to your u0 x. That is, the initial condition is also satisfied. And therefore, this is, in fact, is the unique solution of this partial differential equation. Is that right? So this is called the method of characteristics. Now you see this equation, although it is linear, but I tell you it is extremely important. It arises in a large number of physical processes. For example, if you think of suppose you have color or etc. or some pollutant is spilled in a stream which is moving from left to right with a constant speed, right? Then the evolution of u, this is the concentration of that pollutant is governed by such an equation. It is called advection equation. And the solution, in fact, it is given by this result. This is extremely important. Not only that, you see, in PhD level courses, we discuss the solutions of the Euler's equations. Euler's equations of fluid dynamics. The Euler's equations of fluid dynamics, you see, when they are linearized, in fact, they admit a solution of this kind. They admit a solution of this kind. So anyway, we'll come to that later if the time permits. But this is what I wanted to explain, that how beautiful is this method, number 1, and how quickly it yields the result, right? So this is applicable, this is to be remembered, it is applicable to linear equations, semi-linear equations, quasi-linear equations, and in fact systems, because higher order equations can be expressed as first order systems. So it's a very powerful method, right? Now you can see in the physically what's happening here. You see physically what's happening, that this is your xt plane. This is your xt plane, and these are the characteristics. These are the characteristics, right? Emanating from each point of the real line, as we have seen here, a typical characteristic. If I allow psi to vary from minus infinity to plus infinity, right? If I allow this to vary on this real line, then I get a family of characteristics. And in fact, these characteristics, that's why you see I'm eliminating psi. So psi element of this, it gives me the required solution. That is union of all these characteristics. In fact, it yields the required solution. So if suppose this is your initial data, if this is the initial data, then at time, this is suppose at time t equal to 0, u is equal to u naught x. Suppose this is your u naught x, right? This is your u naught x. Then at time t is equal to t naught, suppose t is equal to 0, I say that t is equal to t1. At t is equal to t1, what happens? I can see here that this is the solution at time t equal to 0. The solution at any time t can be obtained just by displacing each point on the profile a distance c naught t towards right. It's very simple, c naught t towards right. So the solution in fact would be, in this case, it would be like this. U remains the same, u naught, right? U is equal to u naught x minus c. Only each point on the profile is displaced a distance c naught t. So here, this distance in fact is c naught t as a matter of fact, like this. So it goes on, right, like this. In other words, you see, I can show it like this. If this is your initial profile at time t equal to 0, profile at time t is equal to 1 will be obtained from here, but just by displacing each point on the profile a distance c naught t towards right, right? Here, so this point will shift to this point, right? This is your c naught t. Each point, this distance, right? C naught t. Solution at any time t1 can be obtained from t equal to 0 by displacing each point a distance c naught t1 towards right. Okay, very simple. And in this, that is the initial profile is transmitted from one part of the medium to another part without any change in its shape, without any change in its, whatever the, yes, amplitude at each point. You see, you can see here, this remains the same. This remains the same. So there is no change in its shape, there is no change in its speed. The initial profile is transmitted from one part of the medium to another part without any change in its, say, at any two stations, you see, for example, which are at a distance d apart, the same signal would be recorded after a time lag of d by c naught. Because each point is translated, each point is moved a distance c naught t towards right, right? So it's very clear that in linear case, so this is the situation. If the difference allocation is linear, homogeneous, right? The right-hand side is 0, linear homogeneous, then it goes without any distortion. I mean, the profile propagates from one part of the medium to another part without any change in its shape. So it's very clear. If you look at the solution, this solution represents a wave phenomenon, right? If you look at the solution, the nature is that of a wave phenomenon. That is something which is transmitted from one part to another part without any change in its shape and speed. Right? This is what happens in sound waves. So, see, such a difference allocation is said to be hyperbolic. Why it is called hyperbolic? You see, the basic idea underlying hyperbolicity is that Cauchy problem is well posed. What is this? It's a Cauchy problem. That is, we are interested in finding out the solution of this differential equation satisfying this initial data, right? This is Cauchy problem. Cauchy problem asks for determining a function which satisfies this differential equation identically and takes on some specified values on it, right? This is your Cauchy problem. And if the problem is well posed means solution exists if it is unique and it depends continuously on the initial data, we say it is well posed. If it is well posed, right? So the hyperbolicity and well posedness, these two are important things, okay? So this is, now we will talk about what happens when it's, it's not that simple. It's not that simple. You see, we have considered the most simple case. Nothing can be more simple than this. This is the simplest case. Okay. So, let's take a slightly somewhat, I think this is a first order x, y, u, ux. I just wrote b of x, y, u, uy, and this is your c, which is your x, y, u. So given a partial differential equation and some initial conditions, they say, for example, if I write that u at y is equal to say phi x, okay? Say y is equal to say y of x, some function of x. This is some function of x. This is the initial condition which is specified. Okay? So this is a Cauchy problem as a matter of fact, right? Problem is to find out the solution, right? We want to find out the solution of this partial differential equation satisfying this initial data. This is the initial condition. So it's a Cauchy problem, right? Cauchy problem. So how to proceed? The first step is to look for the characteristics. So now we will give a general definition. There, just by inspection, we noticed that C0, if I look for certain curves, which are the solutions of dx dt is equal to C0, then I can write it. I know the characteristics and I can write this in the characteristic form. But what is the definition, the general framework? So now look here, it's very clear that solution of this differential equation is going to be of the form u is equal to u of xy. Is that right? Hello? The solution of this differential equation is going to be of this form, right? And therefore, if I define this as some function, say x, y, u, just transposing this to the right-hand side, say u, x, y minus u. This is equal to 0. I mean, this function I define like this f. Is that right? Then what is your fx? Fx will be your ux, fy will be your uy, and fu will be your minus 1. Is that right? So grade f, this grade f is nothing but this vector ux, comma uy minus 1. Is that right? Looking at this partial differential equation, yes, it's very clear that its solution will be of this form, right? That is surface in the two-dimensional surface, okay? This is x by u space, surface in x by, right? U is equal to constant. U is equal to some function of x and y. This represents a...
Sorry to interrupt you, sir.
Yes.
Sir, some participants want to ask why the previous differential equation is hyperbolic.
Yes. So, you see, there are physical reason, I think it is very clear. Because when I say that deva u, deva t minus c naught, deva u, deva x, right? Hello?
Yes, sir.
A solution of this is a solution of this. Is it all right? Hello?
Yes, sir.
So it is very clear that, I mean, from physical point of view, but the definition is this: an initial value problem, right, which involves a partial differential equation and initial condition, right, is said to be hyperbolic. That is, that partial differential equation is said to be hyperbolic if the Cauchy problem has a unique solution, or you can say it has a unique solution, or rather, the solution is well posed, okay? That is, solution exists, it is unique, and depends continuously on the initial data. So this was an initial value problem, right? This was an initial value problem. If we can show that its solution exists, it is unique and depends continuously on the initial data, means Cauchy problem is well posed because the function satisfies this identically and satisfies the initial condition as well. So what is the definition of hyperbolicity? The basic idea underlying hyperbolicity is this, that the Cauchy problem is well posed. Is it clear? Hello?
Okay, sir. Thank you.
All right. So coming back to this, its solution has to be of this form. So you can see here, if I define a function like this, then the gradient of f, it has this coordinates. And as a result, I can write this differential equation as the dot product of two vectors, a, b, c, and this is your ux, comma, uy, comma, minus 1. Is that right? This differential equation can be written as the dot product of these two vectors. This is one vector having the components a, b, c in R3. What is R3 here? X by u space. This is x, this is y, and this is u, x by u space, R3. So this is a vector field in R3, and this is another vector in R3. Is that right? Is it okay? Dot product of two vectors, A dot B. If A has the components A1, A2, A3, and B has the components B1, B2, B3, then what is A dot B? Hello? If the vectors A and B have the components A1, A2, A3, and B1, B2, B3, what is A dot B?
It's simple.
That is mod A mod B cos theta.
In terms of components, you see, if A is a vector.
That is, yeah.
Right.
That is simple A1, A2 plus B1, B2.
Right. So similarly here, you can see here that this is a vector and this is another vector. The dot product will be A1, A2, that is AUX plus BUY minus C equal to 0. Is that right?
Yes, sir. Yes, sir.
So what I again repeat, this is a given differential equation. These coefficients are known to us, A, B, C, they are given to us. So these A, B, C, these coefficients, they constitute this vector field. Is that right? A, B, C, this vector field. And UX, UY minus 1. Can somebody tell me what does it represent? UX, UY minus 1? Hello? Hello, what does it represent geometrically? It is nothing but gradient f, I have just said. I have just mentioned it. It's very clear. This is a surface. Right? F is equal to 0 is a surface. F is equal to 0 is a surface. And its gradient, it has the components ux, uy minus 1. And what does it geometrically? What does it mean? It gives us the direction of the normal to the surface at any point. Is that right? So the dot product of these two vectors is 0. What is this vector? It is normal to the surface, to the solution surface. This vector is normal to the solution surface, and therefore this vector field must lie in the tangent plane at that point. Yes or no? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Yes. So a wonderful geometrical interpretation that a given partial differential equation, what does it represent? It represents, as a matter of, it's very clear from here. It can be described as determining a direction field in the R3. This is your direction field. This is the direction field which lies in the tangent plane to the solution surface, because this is normal. So this direction field lies in the tangent plane to the solution surface, right? So the differential equation may be regarded as determining a direction field. A, B, C are known to us, and therefore we know this direction field. Correct? What is the nature of this? This vector lies in the solution surface, as a matter of fact, because if you think of a point in space, x by u space, which starts from a given point in such a manner so that tangent at each point coincides with the instantaneous direction ABC at that point. Is that right? A, B, C, they are given functions. So we know how do they behave, you see, in the x by u space. If the point or think of a particle, if it moves in x by u space in such a manner so that starting from a given point, right? Starting from a given point which lies on that surface, what happens? What happens? The point, in fact, or you call the particle, will trace a curve in x by u space, right? And this curve will be referred to as characteristic curve of the partial differential equation? Yes or no? This is a geometrical picture. Is it clear? Starting from a point, right? Starting from a point which lies on the solution surface. Now, if the point moves in the x by u space in such a manner so that the tangent at each point coincides with this vector at that point, it moves it so that at each point it coincides with ABC at that point. Is that right? If the particle is moving or the point is moving in such a manner so that the tangent at each point coincides with the instantaneous direction of this vector field at that point, a space curve would be traced out. Yes or no? And this space curve is called the characteristic curve of the differential equation, and this characteristic curve will lie in the solution surface. It will lie in the solution surface. Okay? If this is your, right? If it moves in such a way so that the tangent at each point coincides, right? Tangent at each point coincides with the direction of this vector field, then because this lies in the tangent plane, and therefore all these characteristic curves will lie in the solution surface. Is that right? And in fact, the union of all these characteristic curves will be nothing but this solution surface. So characteristic curves geometrically you can picturize that they generate the solution surface, they span the solution surface. Is that right? Hello? Is it okay?
Yes, sir.
All right. So, so this method, so now perhaps we can, what is the definition of characteristic curve now? The tangent at each point. So if I say that x is equal to x of s, y is equal to y of s, u is equal to u of s is a curve, right? It is a curve. Let me call it ch or simply c, right? S is the parameter along this curve, the locus of a point which depends only on one parameter, right? This represents a curve in space. Is that right? Hello? This is the parametric representation of a curve which is such that ds is equal to a, dy ds is equal to b, du ds is equal to c. What does it mean? It means that this point is moving in x by u space in such a manner so that tangent, because dx ds, dy ds, du ds, these are the components of the tangent vector to the curve at any point. Is that right? Hello? If r is the position vector of a point having the coordinates x, y, say u, right? And suppose x is a function of s, y is a function of s, u is a function of s, right? Then what is your drds? Hello? Drds will be your dx ds, dy by ds, du by ds. And what does it represent? A vector tangent to this curve, right? A vector tangent to this curve. And I have just mentioned that it is that curve such that tangent at each point coincides in the direction of this vector. So dx ds is a, dy by ds is b, du ds is c. These are called the characteristic curves of the differential equation. Is it all right? Hello?
Yes, yes.
So given a differential equation, quickly I can write the characteristic curves, right? And this is your, what does it represent? Initial condition. If you look at the initial condition, what does it represent? Hello? This is, you see, if you look at it, it is the intersection of two, hello?
Yes, sir. Yes, sir.
Yeah, so it's very clear. I can give a parametric representation to it, right? I can give a parametric representation. Suppose I take this as ux0 is equal to say u naught x. I take this curve to be the line t equal to 0. Very special case, okay, for the sake of simplicity. What is this? Y is equal to 0. Y is equal to 0 means here, all right, this is your y, so means x-axis. Y is equal to 0. Is that right? So I can give a parametric representation to it. I will call it, this is the initial condition, that is x is equal to xi, right? Y is equal to 0, And what is this? U is equal to U naught of xi. This is xi is the parameter.
Sorry, sir, but screen is not visible.
Hello? Yeah, what's the point? Oh, sorry. Is it all right now?
Yes, sir.
All right. Okay. So this is the initial condition. So initial condition, this is the curve which is specified, right? It is a curve. This represents a curve. X is a function of xi, y is a function of xi, u is a function of xi. Of course, here it is 0. So definitely this represents a curve. Okay. So, hello. All right. So the thing is this, that the Cauchy problem. Now, what is the way how to get the solution? How to get the solution surface? The solution of the Cauchy problem. This is the Cauchy problem. What is the way out? You think of this given curve, right? And allow these curves to emanate from this. Okay, this S is the parameter. S is the parameter along the characteristic curves, which emanate from these points. Xi is the parameter along gamma, and S is the parameter along characteristic curves. Is that right? This is your correct, right? This is a characteristic curve. CH. S is the parameter along this. Gamma is this initial curve. Initial curve is a fixed, right? So the Cauchy problem, as I just said, it asks for determining a function which satisfies the differential equation identically and takes out some specified values on a given curve. This gamma is a given curve. Gamma is a given curve. All right. So you see, only 3 minutes are left. I think we will continue next time. If there is any query in this, please let me know. This is very important. You see, this is the geometrical configuration, the geometrical picture of, how we are going to use the method of characteristics, correct? So I have explained that what the characteristics indicate. What do they mean? It is an integral surface, right? What do we mean by integral surface? When we say the integral surface of a vector field, means the surface is tangent to that vector field at every point. So it means the characteristics, they are the vector fields. Hello? The characteristic curves, they are the integral curves. What are the mathematical definition? What are the characteristics? They are the integral curves of the vector field, right? At every point of this, the tangent at every point is parallel to this vector field. Dx is A, dy by ds is V, du ds is C. So these are the integral curves, and in fact the solution surface is the integral, right? That is the integral surface, because it is tangent to the vector field at every point. So the best way to find the solution of a Cauchy problem is to consider characteristic curves emanating from the different points of this given curve, right? From every point on gamma, right? Every point on this. Okay, and then the union of all these sweeping out a surface, and that is your solution surface. Perhaps the procedure I will discuss next time. So the time is up now, it's 5:59. Is there any query with regard to this? I would be happy if there is any question. Hello? Is there any question?
Yes, participants, you can ask your questions if you have any.
Sir, one of participants asked how solution surface is created geometrically.
How solution surface is generated geometrically?
Yes, sir.
Yeah, that's right. I just mentioned that the best way is to think of characteristic curves emanating from this initial curve, and the union of all these characteristic curves, all these characteristic curves, they sweep the solution surface, right? They constitute the solution surface. This is the whole idea.
Thank you, sir.
So mathematically, how it happens, I will discuss tomorrow. Okay, that is union of all these characteristic curves. In fact, this is your solution surface. So we say that these characteristic curves, they span the solution surface. Just now you see, did you notice that in first, in the simplest example, this is the characteristic, typical characteristic, right? For this dy u, dy t plus c naught dy dy x. So what are the characteristics if I allow xi to vary from minus infinity to plus infinity? Yes, this is the, yeah, right. So these characteristics, as a matter of fact, they will generate, because what happens to u naught? U naught remains constant on each characteristic. So whatever the information is available here, it will propagate along this. Whatever the information is available here, it will propagate along this. So u is equal to u naught of x minus c naught t. That is union of all these. I have eliminated this xi, is the parameter, right? This is the variable xi, is varying from this to from every, right? So eliminating this, in fact, we are integrating all these characteristics to form a surface, and this is the mathematical equation or the form of the surface. U is equal to u naught of x minus ct, or u as a function of x and t.
Sir, there is one more question.
Yes.
Is there any difference in characteristics and characteristic curves?
Pardon?
Sir, is there any difference in characteristics and characteristic curves?
No, same thing. Sometimes you say characteristic curves or the characteristics of the differential equation, it is same thing, but it is better to call it a characteristic curve of the differential equation.
Okay, sir.
Right? In short, we say that when the characteristics intersect, what are these characteristics? They are the characteristic curves. Right? So in short, we say characteristics, but what are these characteristics? They are the characteristic curves of the differential equation. Is it all right? Hello?
Thank you, sir. And one question is, what is the classification of the Cauchy problem if it is not well posed?
Again, repeat. What did you say?
What is the classification of the Cauchy problem if it is not well posed?
No. We will not call it a hyperbolic. I mean, if the problem is not well posed, it is meaningless. I mean,
okay, sir.
Hyperbolicity means Cauchy problem is well posed for that partial differential equation.
Okay.
With respect to given initial condition, this is the meaning.
So there is one more question.
Yes.
Yes, ma'am.
No, Praveen, you should read out.
Okay. Sir, there is one more question.
Yes.
Is there any notion to characterize first order PDEs as parabolic or elliptic equation?
No. I just illustrated in this case because it is hyperbolic. I can factorize it. Take care of it. Yes, please take care of your mic. All right. So is it okay? Hello?
Yes, sir. Yes, sir.
So can we close this session? Professor Chaudhary, can we close this session?
Yes, sir. Sure, sir.
Yes, sir.
Okay, all right. Thank you.
Thank you, sir.
So tomorrow.
Thank you, sir, for your. Yes, 5 p.m. again tomorrow.
All right. Okay.
And thanks again for your very informative, elaborative presentation. I hope everyone has followed very nicely.
No, I will
see you again tomorrow at 5.
Yes. I will repeat everything so that everybody understands.
Yeah. We want to get everything clear from you, all our participants.
Very good. Okay. Thank you.
Thank you, sir. Thank you once again. See you too. So I think Professor Kapil Sharma is with us. Oh, yes, okay, sir. So next lecture is with Professor Kapil Sharma. Before he starts, let me give a brief introduction. Professor in the Department of Mathematics, South Asian University, New Delhi, Professor Kapil Sharma completed his post-graduation from Kurukshetra University and PhD from IIT Kanpur. With his many research publications and 20 years of research, teaching and research experience, his research areas are numerical analysis, singularly perturbed problems, partial differential equations, and functional differential equations. He also received, he actually is the recipient of one very important award, which is postdoctoral award, INRIA France, National Institute for Research in Computer Sciences and Automation, France.
Yeah.
So now over to you, sir, for your lecture. Professor Kapil Sharma, now you can start your presentation. Good evening, everyone.
Good evening, ma'am, and thanks for giving a nice introduction.
Sir, you were there with us in recent past for one lecture.
Yeah.
You are a family now.
Deliver a lecture, and it was very, useful interaction.
Yeah.
But if it would be offline, so then things would be the different.
Yeah.
But anyway,
we know, sir. There's a difference between online and offline.
Yeah, we have to survive.
Yeah, one-to-one interactions I have some else charm we could have participants would have been more benefited in that. Anyways, now it's a pandemic period, so we have to work with online.
Sure,
sir. So now you can start. Yeah,
from this pandemic
soon, and then we'll again meet you somewhere.
Sure, ma'am. So I think
now you can start.
Yes, ma'am. Sure. So can I share my screen?
Yes, you can share your screen, sir.
Yeah. So share screen. Just a moment. Which file I want to? Yeah, so ma'am, it's visible?
Yes, sir.
Yeah, so I have, I think, 4 lecture. Am I right?
Yes, sir.
So I will try as much as I can cover in this lecture. So the basic task which has been assigned to me is to give some enlightenment on the numerical methods for initial value problem. Am I right, Harindri ma'am?
Yes, sir.
Yeah. So I will start with I think the participants are new or?
Sir, they are teachers working in colleges in Delhi or outside Delhi.
Colleges, and also so some part of my lecture will be repeated, which I already given. I hope that there are the audience are new also.
Yes, sir.
So I will start basically my lecture from the beginning, that the numerical evolution of numerical methods for initial value problem. So first we should understand that why we are doing, and we will study these methods in a way that not just a formula, that how these type of method might have evolved that time when they were researched. So it will not only give you a flavor that about these methods, but also give you a flavor that how we should narrow down our problem to do the research. So I will try to convey this in during these I mean lectures. And the main book which would be followed during this these lecture will be by this the very renowned numerical analyst Professor J.D. Lambert, Computational Methods in Ordinary Differential Equation, published by Wiley. So mainly we will cover part from this book. So first I will talk about that. So ma'am, I mean, in this also we have one way delivering, or participant can also interact.
So they can ask questions and you can take their doubts if they have any.
Okay. If they have some doubts, so they can
put up in the chat box and you will later on.
Okay, chat box. But I mean, we cannot interact right now. Means suppose I want to ask some question from
Sir, you can, no issue.
So they can respond.
Yes,
Am I right?
Yes.
They can switch on their mic and they can.
Their mic and they can respond.
Okay, good. So in that way, we will start with the numerical. First, I will try to explain that what is a numerical analysis, and then the motivation for that. And basically, I will start from the motivation towards the mathematics, and then why we do the numerical analysis. So first, I will explain what is numerical analysis, and then how this is important. So numerical analysis, analysis is consisted of two components. Number one component is the development of method to find the approximate solution of a mathematical problem or mathematical model. And number two, the analysis of error occurred in the approximation. Am I right? So there are two components. Why it is numerical means we can say that finite numbers and analysis. So it is consist of these two things. In the first one, we are talking about the development of methods to find the approximate solution of a mathematical problem. And the second important component of the numerical analysis is the analysis of error occurred in the approximation. When we talk about the approximate thing, so surely there would be some error. So that must be analyzed. So first we will study that why we should do numerical analysis. What is the need of that? So anybody can respond. Yeah, please try to make this a little bit interactive. So if anybody have any, idea in mind, so please. Okay, so just tell what is a motivation to study mathematics. Anybody can answer, any participant?
Sir, if we are not able to find the exact solution of a problem, then we find the numerical solution or the approximate
Yes,
solution.
approximate. If you cannot solve any problem, then we find the approximate solution using these methods.
Yeah, very rightly. Yeah, if we don't have any method exact solution, so then we should go for the approximate solution. So first we have to understand that whether this approximate solution or approximate information is sufficient for us. First we should justify that, and even before that, whether it's the feasible things or feasible, or I should say that if in most of the situation we are in position to find the exact solution, so then nothing to worry. So then why we should go for the approximate things? Because what is our basic motive to solve a mathematical problem? I think one way is that for the fun we are doing, but that is not the things. In most of the situation, why we solve that? We first convert a real life problem into a mathematical problem. Then rather than solving the our basic motive to answer the real life problem, but to answer the real life problem there are more than one ways, but the best tool by which we can do a realistic answer, so that is using the mathematics. So using some mathematical concept, we convert a real life problem into a mathematical problem, which we call mathematical model. This thing is clear. Once we have converted that model, then we talk about the well-posedness of the mathematical model or mathematical problem. Once we have done that, so then we can say that either you solve this real life problem or corresponding mathematical problem. So whatever answer you will get from the mathematical problems, you will have the answer to the real life problem. So in that way we do that. So the next thing, once we study the well-posedness means in the sense of hardmark, if you are aware that we say that a mathematical problem is well-posed. Number one, it has a solution. Number two, the solution must be unique. Number three, the solution must be stable in the sense that it continuously depending on the
initial values,
on the given data. It's fine. Given data here, the condition is this, and what are the given thing? If we talk about in this platform, y prime is equal to fxy, y x naught is equal to y naught, this f and y0, these are the given data. So then we say that the problem is well posed. So that's I'm just giving you a very toy example. All of you are aware, but I am telling you that how we convert a real life problem into a mathematical problem, and then we will talk about the numerical approximation, and then we come to the in the platform of initial value problem. So now how we do that? For example, I am giving you, I think all of you are being a student of mathematics, so aware about or heard the heat equation. So what is a real life problem? And then I will tell you that how using a mathematics we model this phenomena. So basically our real life problem is that, what is our real life problem? Our real life problem that suppose we are heating a road. We are heating a thin road. So then what is my real life problem? My real life problem is to measure the temperature of the road at different point and at different time. Because the point which are closer to heat source, so they have more temperature than the point which are of the road which are far from the heat source. Am I right? One thing is this. Another thing, as time passes, the temperature of the road increases. So my task that at different time and different point, I want to measure the temperature of the road. So the one way is that using a thermometer, I can measure that, but it is not realistic. It is not realistic because the road has infinitely many points, and also time direction also you have infinitely many time. Suppose somebody interested at 10 o'clock, 10, 10:01, 10:20, 10:25. So in that way, so it could be, but it is very cumbersome, and in certain situation it's unrealistic. So how we do that? So using some mathematical concept and physics of the problem, we convert this problem into a mathematical model. Now look, suppose let you be the temperature of the road. Being a student of mathematics, so that is a best way. Let us assume that you be the temperature. You be the temperature of the road, road at the point, because it's a depend on temperature, depend on 2 point, x and t. X is the distance from the heat source and t is the time. So at time x and x comma t, it's fine. So now if we look the physics, what's happening? Basically we are giving we are giving heat with respect to time, and what's happening, and this heat basically diffusing with respect to x. Am I right? Because in the as heat by the heat source, it's going to the road, to the system, and then it is diffusing. Am I right? So we can say that the rate of change of temperature basically is proportional to the diffusion with respect to x. So curly u by curly t is proportional to curly 2u by curly x square, because the diffusion is represented by the second derivative, and rate of the change of temperature is represented by the first derivative. So if I write, I mean denote in the another notation, ut basically is proportional to uxx, and we can say that, if you might have remembered, ut is equal to alpha or cuxx, where alpha is the diffusive coefficient, which depend on the material of the road and this and that. So in that way, so basically now we have one equation, we constructed one equation, and of course we are interested in the one unknown. But the problem here is that this is not in the unknown. Basically this is in the its derivatives. Am I right? And ut is equal to cuxx. So if you, so now what is a way to get rid of, once you have the derivative, so you want to have the, the unknown. So what is the way? Just integrate that. So once you integrate, so how many parameter would involve in that? Because there is one derivative with respect to time, and another two derivative with respect to space. So in x direction we called space, and t with the time direction. So we generally use this terminology. So in the direction of x, there are two derivative uxx, and in time direction we have one derivative ut. So basically when you integrate, so you have three parameter. And if you just integrate this differential equation, partial differential equation, so you have three.
Excuse me sir, sorry to interrupt.
Yeah, please.
आपका स्क्रीन फ्रीज हो चुका है, शायद वो दिख नहीं रहा participants को.
No, but actually now just
you are explaining first.
Yeah, I'm just explaining first, because we will start basically the initial value problem. So just this is, I'm giving you the background. So I hope you people are able to follow.
Sir, you are writing somewhere or only explaining?
No, I'm not writing.
He is explaining only, Chandrasekhar.
I'm just explaining.
Somebody are asking, sir is writing somewhere. That's why I'm asking.
No. But actually, I wish to write, but it's very difficult. Or I can use the board if anybody. one.
Okay,
But,
sir, no problem. No
so,
problem.
are you able to follow me, or should I write, sir?
Sir, you can explain, no problem.
Yeah.
If
So
you are able to write, then okay. Otherwise, no problem. You can explain.
I can try, but it's very. I mean, okay. Just I'm trying. If I would be able to do that, so then it would be very good. Otherwise,
yes, you need
multiple screen we can do that. Yeah. Again. Yeah. Here I can use that. Yeah, so basically a problem all of you have understood. So ut is equal to, basically, now it's visible, sir?
Yes, sir.
Yes, sir. Yes.
Yeah, alpha u x x. So now we, if you talk about once is, so as I told you that first of all we will talk about we have convert. I think all of you are agree that our objective to find this u, once we have assumed that let u be the temperature, be the temperature of rod at the point x comma t, or t comma x, whatever you are taking, x comma t. So it means that basically this was our real life problem was to measure the temperature of the rod at the point x comma t. Being a student of mathematics, we have assumed that let u be the temperature of the rod at x comma t. Now it's fine. So now our task is to find this u. Am I right? So to find u, we need one, because one unknown is there. So we need one equation. And using the physics of the problem, we have converted this, because I told you that what's happening basically, it's a heat going in the system, in the rod, and that is diffusing with respect to x in the system. So ut is proportional to uxx, and we have taken ut is equal to alpha uxx. So alpha, I mean, depend on the material of the rod. So now it's fine. But here the problem, what is another problem, that this relation is not directly in the unknown u, it is in the derivative of u. So once we, so this thing is clear. Now we can say that rather than solving real life problems, solve this mathematical problem or mathematical equation. Now we will talk about its well-posedness. So first we will talk about its existence and uniqueness of the solution. So and then we go for the solution methodology. So when we talk about the solution of this problem, so if we integrate that under certain condition, of course, so when we integrate this problem, so one thing, if you observe that, so if that this equation is meaningful or not. So for meaningfulness, that u must belongs to c1 means its first derivative with respect to time must be continuous. First thing is this should be, and in the right hand side, that it's a second derivative with respect to x must be continuous. So then it belongs to, we can say that then this problem, this equation has a meaningful, it's both have the meaning. So now the second thing we talk about its solution. So now when we integrate this, so there will be three parameters would be there, with one, because of this t derivative, and 2 because of when you integrate with respect to x, so you have 2 from the x. So that's why. So but we have to have a unique solution for the well posedness of the problem. Uniqueness. So for uniqueness, what we need to have, we need to fix all these 3 parameters. And to fix these 3 parameters, what you need to have, you need to put 3 conditions. Am I right? We need to put 3 restrictions on the solution. Am I right? Suppose I ask you that, okay, go from Akbar Bhavan to Akbar Bhavan, Chanakyapuri to the Connaught Place. So there are, I mean, more than one way would be there. There are more than one way. If I put the restriction that, okay, go via Asoka Road or this and that, so in that way I can fix, I can restrict you to going in a one way. So then I have to put some restrictions. So same thing here. If you observe that there are infinitely many solutions it has, but I am interesting to have a unique solution, because suppose we solve this and we say that, okay, the temperature of the road maybe this one, maybe this thing, maybe there, so you would be confused. You would be interesting to have a unique way or one value you want when we model a real life problem to answer that. So in that way we need to put the conditions. So we basically put one condition for the time, and where we put these restrictions, basically boundary of the domain. Am I right? At either at the initially we can do that, because in the when it's going in the domain, so we don't have the control, but initially or at the boundary we can control the situation. So that's why initially we assume, let us assume that initially means when time is 0, or x comma, because I have taken x comma 0 is equal to suppose it's a function of x only, u0 x. So initial temperature profile of the road we know, and the 2 conditions. Suppose the this is x varying from 0 to length of the road is 0 to L. So we can have that at u0 t is equal to say, you can capture the both hand at the freezing 0, and another condition you can put this L comma t is equal to 0. So now look that this differential equation, and then these 3 conditions will fix, and under these this differential equation, under these 3 conditions, it has a unique solution. So it means that now the problem is well posed. This thing is clear. So now we solve this, and this is known as all of you are aware that this is a heat equation. So whatever solution we are getting, so what type of solution we will get? So our uxt will be uxt will equal to say some function of x and t. Am I right? gxt, where g is a given one. If all of you are aware about the solution, and fortunately for this problem we have the exact solution, but generally it doesn't happen. But fortunately for this we have, and you take any value, once you found this G, so put any value of X and T, so you will have the answer. Suppose I want to measure this at 0.5, I am taking the value of X is 0.5 and T is 2. So then just put in the formula, and this will be G 0.5, comma 2 will give you the answer, because G is a known function. So you just put the X in place of X 0.5 and in place of T 2, because some combination of X and T would be there. So in that way we will find the answer. So in that way we solve the problem. So any doubt till here?
Sir,
Yes,
there is
sir.
one question.
Yeah,
One
please.
participant asked if the boundary condition are non-homogeneous, the problem will still be well posed.
Yeah, of course it would be well posed. It could be then also well posed in that case, problem. But our problem, I mean, our basic motive here not to study this problem. Our motive just to explain that how we use mathematics to answer the real life problem. You can go and study heat equation, and there are a lot of literature. But of course, if you have some constant term is there, of course, so then it also has a solution. So my basic motive to deliver this is that how we use mathematics to answer the real life problem. So regarding this, any other question is there, or should I move further?
No, sir, no question.
Okay, thank you. So now we are moving to we are coming back that as I told you that fortunately for this particular problem we have a procedure by which we can find the exact solution of a mathematical problem. But I am now making a claim that in most of the situation, the mathematical problem which model our real life phenomena are very, very complicated in nature, and we don't have any procedure. We do not have any procedure to find the exact solution of the problem. So then what we should do? Then either we should leave this, but I am saying that most of the, if it could be 1 or 2 or maybe a less number, so then we can leave that, we can explore some other. But I am claiming that in the most of the situation, it is not feasible. Till now we don't have any procedure, or we are not in position to develop a method by which we can find the exact solution. So another thing, okay, rather than finding the exact information or exact solution, so can we find the approximate? Yeah, wherever we are facing the problem, we trying to approximate that, and we will solve the approximate problems. Of course, then in that case we will have the approximate information. So now another, I think, question we should ask, whether this approximate information serve our purpose. I'm making another claim. What is the another claim? Another claim is that in most of the practical situation, the approximate information serve our purpose. Am I right? I'm giving you some example. I think you would be also convinced. For example, in the weather forecasting, suppose in a raining season, I'm planning to go outside. So the information whether it's a raining day or non-raining day, this information is sufficient for me, that how, rather compared to how much raining it would be or not, or maybe more precise that whether it would be heavy rain or or less rain, this information is sufficient rather than how much it would be exact. Suppose we wish to some policy maker need the I mean prediction for the population, population forecasting after 10 years. 10 years. So rather than the exact population, if it would be, they would be known that approximately this would be the approximation, I mean the population of Delhi after 10 years. So this information is sufficient for a policy maker. Am I right? In financial forecasting, the information that in the near future, whether the market in the upward direction or downward direction, this information is sufficient for an investor. If the market will be in the upward direction, then investor will pour the money in the market. If it is in the downward direction, so then he or she can withdraw the money. Am I right? So I am claiming, so I think in the most of the practical situation, the approximate information is more than sufficient to serve our purpose. So that's why we should go for the approximate method. So that's why I'm telling you that numerical analysis is consisted of two components, and one component is the development of the methods to find the approximate solution of a mathematical problem. Now, okay, so the first component is justified to study. Now, why we should study the second one? Why we should analyze the I mean the error? Because we are saying that at the beginning that in the we will do the approximations. Of course, error would be there, because when we are developing a method, so with the method we should tell that this method has this much error. And now it depends on the user whether this method suits to him or her other or not. I'm giving you one instance for this also, that suppose I wish to predict that from Chandigarh to Delhi, I plan to my journey from Chandigarh to Delhi, and it takes, let us assume it's take 5 hours. But if somebody, madam says that, okay, I ask madam says that it will take 4.5 or 5.5. So this 4.5 and 5.5, this information is sufficient for me. So here I am tolerating error roughly of order 10 raised to the power minus 1. But there is one instant during the Gulf War, there was a failure of Scud missile of US, and because of that a number of casualties were there, and then they analyzed and they found that there was error of order 10 raised to the power minus 8. So I mean to say that at one instant we are not tolerating of error of order 10 raised to the power minus 8, and on the other side we are able, or we are tolerating the error of order 10 raised to the power minus 1. So that's why, suppose we have two methods. One method has the error of order 10 raised to the power minus 4, and other method has error of order 10 raised to the power minus 10. So the if I ask somebody which I should use, so I mean one can say that okay, the best one 10 raised to the power minus 10. But at the same time we know that there is no free lunch. There is no free lunch. Free lunch theorem says there is no free lunch. If you are getting something, so certainly you have to pay for that in the sense of some other thing. So that's why suppose I want to use that method to to plan my journey. So in that case, I can use that easily. But if I want that, to use that method in simulation of the Scud missile, so there I cannot do that. So that's why I will use the method which has the error of order 10 raised to the power minus 12. So that's why whatever error occur in the approximation, that should be analyzed. So this thing is clear, I hope. So now it's you are able to see this screen, y prime is equal to fxy, or still you are seeing the board?
Board, sir, board.
Okay, so I have to stop because now I want to share this one. Stop sharing, I think. Again, I have to share the screen. Yeah. So now we talk about this the initial value problem. Now we talk about the initial value problem. Y prime is equal to fxy and y at x0 is equal to y0. So of course when I'm saying this is a initial value problem, first derivative is involved here, and with this I mean to get rid of the one parameter, so we have one condition. So now we talk about the well-posedness of this problem, and for that first we will talk about existence and uniqueness of the solution of this initial value problem. Am I right? So I think all of you are aware about the existence and uniqueness of this problem, initial value problem. And under certain condition on F,
Yes,
on
sir.
F, this problem has a unique solution. So now we come to the solution. So first we will try to find the exact solution of this initial value problem. So anybody can answer what will be the exact solution or of this initial value problem, who did not attend my previous lecture? Yeah, anybody can answer? Yeah, the answer is negate. No, we don't have any procedure by which we can find the exact solution of this. Maybe in certain particular form, particular value of x we can find, but in general we don't have any procedure to find the exact solution of this initial value problem. So I'm just making this claim. For the journal value of f, of course this f has the sufficient regularity to have the existence and uniqueness of the problem, but still we don't have any procedure which give the exact solution of this initial value problem. So then we should develop the method to find the approximate solution of the initial value problem. So now I need again new sharing. Clear, I think. Clear all drawing. So now here also we will start by assuming let let y
Sir,
be
one of the participant asked if variables. Excuse me, sir.
Oh, yeah, yes, ma'am.
Sir, one of the participant asked if variables in fxy can be separated, exact solution can be found.
So that's why, ma'am, I said that for some particular form of f we can find, but for in general we cannot find.
Okay.
Am I right?
Okay.
Yeah. So that's why for some some particular, suppose you take constant, so then you can integrate that easily.
Yes.
Even non-linear function also. So f has form y power n. So in that case also we can find the solution for the non-linear one. But of course, if it has a separable form, so in that case, but in general we cannot find. Am I right?
Yes.
Yeah.
Yes.
So now we start. Let y be the solution. Let y be the solution of the initial value problem. The initial value problem 1, 2. Am I right? What does it mean? That y is satisfying 1 as well as 2. So now what is our objective? As in the previous case, now our objective is to find this y which satisfying the differential equation 1 and the initial condition 2. Am I right? So how we start? We start that we will keep y on the left hand side. We will keep y on the left hand side, and we will try to have
सर काइंडली अनम्यूट योरसेल्फ. आप म्यूट हो चुके हैं. कपिल सर.
So you're not audible.
Yes.
Okay.
Yeah. Yes. Yeah. So why we keep y on the left hand side, and where is that? Yeah, here we keep unknown on the left hand side, and we are interesting to have known thing. This is basically y. We can say that y x. Y is a function of what's happening. Where is that? Yeah. From here we can take. Yeah, so y on the left hand side, and we are looking something I mean known thing on the right hand side, and we will try to that. So how much time ma'am I have? It's I have to
Another
finish
10 minutes.
Eh?
Another 10 minutes, sir.
Yeah, so I think I should stop here because or
Okay. The new topic you will take tomorrow.
yeah, because it will take I think 20 minutes more to
Moderators, you
cover. So I'm just giving you exercise. Just try to find out the solution. I'm giving you just the way that
you can take
so
them home.
basically we keep y on the left hand side, and known we wish to have on the right hand side the known thing. Known thing. What are the known thing? X. X is the part of the domain that we know, and also we know that Y at X node. So in that term, if we would have the right hand side, so then our work will be over. So in that way, we will try to generate some methods. So this thing is clear. So you should try to do that, and then you will say that wherever you feel some difficulty, so you can take some approximation. So in that way, we will try to generate the different class of methods. So we will discuss. So anybody, if we have 4 minutes remaining, maybe my watch. So please, if anybody have any doubt, till now. Ma'am?
Yes, sir.
So is there any doubt?
I don't think, sir.
No, sir. No, sir.
No, sir.
Okay,
No
okay.
doubt from participant
Also
sides.
we have
Participants said no doubt.
lecture at?
Yeah, you can conclude, sir.
Yeah, continue at 6 o'clock, 6 to 7.
Yeah, tomorrow at 6 o'clock, you can continue with the same.
Okay,
And you
okay.
have given them the exercise, they'll complete in the meantime.
So tomorrow I will give the assignment also.
Yeah.
So, okay.
Okay, sir. Thank you so much for your this elaborative presentation and of course, practical approach of solving the things. And see you tomorrow at 6 p.m. for another topic. Okay, sir.
Okay, thank you.
Now we conclude, and I thank all the participants to be with us, and with very good participants. We're having patience for everything. So see you tomorrow again at same time. We are starting every day at 5 p.m. and there'll be 2 lectures every day. Again, tomorrow we'll be having Professor V.D. Sharma from 5 to 6. And the next lecture will be from Professor Kapil Sharma, 6 to 7. So be there tomorrow. So it was nice to be with you for this session. So we can conclude now.
Yes, ma'am.
Okay.